I'm Richard. Thank you for letting me come and talk to you today. Let's be real informal. If you have questions, raise your hand. We can go down rabbit trails. We can talk about whatever you want. I mean, I've got a huge deck of slides. Please do download them. It's doubtful we'll get through all of them, but maybe we will. Who knows? And some of them have a lot of fine print, so you may want to download them just so that you can, do the expand thing and read it. Yeah, so let's just get started. I'm the inventor of SQLite. I'm still the lead developer. There's a small team of developers that work on it. There's 5 committers on the project total. And I actually have a PhD, but it's not in database technology. I've never had a course in databases. I studied computational, my dissertation is in computational linguistics. And it's way out of date because it was in 1992. So, and I never intended to be a database guy, but here I am. So it's a pleasure to talk to you. All right, so what is SQLite? I guess you know about it a little bit. It's the most widely used database engine in the world. I mean, within 2 meters of you right now, there's probably about 100 different SQLite databases quietly whirling away, making your life easier. And how did it get that way? Nobody's more surprised about that than me, but how did it get that way? And the big thing the theme I want to give to you is that it solves more problems than it creates. There's another person on the internet recently said, your enemy is complexity. And SQLite is a great way to reduce complexity. It strives to be simple. Now, sometimes you really need complicated things. There are some hard problems for which the solution is going to be really complex, and you can't get around that. But if you can simplify things and avoid the complexity, that's a better approach. All right, so what are some of the distinctive features of SQLite? The first, most database engines are client-server. There's a separate process, or at the very least a separate thread that's running the database engine. And your application, when you link with the database library, that's just a communication hub. It encapsulates the parameters, sends the message over to the database engine computes the answer, sends the answer back to your application, and then you use it. And that works really well, except what happens when the database engine goes down? There's a malfunction. It's misconfigured. It stops working. Then your application can't work. This actually happened to me. I was doing freelance application development, and I had an application that had to talk to an Informix database, and the database was controlled by a different group of people. I had no control over it, but it would sometimes go down, and then my application would say, hey, I can't work, and they would send the bug reports to me because it was my application that was popping up the error message dialog box. So I thought, well, how can we fix this? And I thought, well, why do I even need the server? Why can't I just talk directly to the database on disk? And I looked around, and there were no SQL database engines around that would do that sort of thing. So I said, I'll just write my own. And here we are 24 years later. Here's a matrix of different database engines. On the top, we've got no SQL database engines. And on the right, we have SQL database engines. And no, client server on the right, embedded on the left, SQL below, and non-SQL above. And so there's use cases for all of these database engines. The most common ones you're going to see over on the client server side. Those are the ones that are going to be for big installations. Do you have any familiarity with BerkeleyDB or RocksDB? Has anybody ever used RocksDB? Yeah, you've done that, yeah. So SQLite is kind of unique in that it is the only one where you have a full SQL database that is also embedded or serverless. Another distinctive feature of SQLite is that the deliverable is a single file of C code. Usually, when you have a library like this, you get a bundle of files or something. But we don't. It's a big file. It's 9 megabytes right now. It keeps growing every day. We don't edit that file directly. our source tree has a bunch of small C files, and then our build process glues them all together. But by delivering it as a single big file of C code, if you're programming in C or C++ or Rust, you just add this to your makefile, and suddenly you've got a full SQL database engine embedded in your application. It's very easy to do. And this makes it easier to deploy. Your enemy is complexity. Another big feature is that SQLite has the database is a single file on disk. It can store thousands of different tables, views, triggers. It's very space efficient, but because it's a single file, you can treat it as kind of an application file format. If you're building an application and you need to store some data, you can make an SQLite database your file format. You've got the full power of SQL, transactions, and the query language, but you can store it in a single file. And then when created that file, you can send it to your friends by an email attachment or something like that. People say, well, yeah, but you know, I want to use text for my application file format because I don't want to depend on some opaque binary file. You know, I want to be able to read it. I want it to be lasting. Well, it turns out that the SQLite database is a binary file, but it's an open format. It's been stable since 2004. It has, well, we've added enhancements, but it's backwards compatible to 2004. The complete specification is online. It's readable and accessible. It's about 20 pages, depending on your font size. It's completely cross-platform. It's recommended by the US Library of Congress as a file format for the long-term storage of archival data. And we're promising to support it through the year 2050. So don't worry so much about that. Other people come to me and they say, look, I'd like to use a database, but I need my application to be really fast. I need very fast access to my application. I can't have an SQL database engine in between me and my data. It will slow things down too much. Turns out, you can actually get data out of an SQLite database faster than you can read individual files on this. This is a study we did for a cell phone manufacturer where they have a bunch of thumbnail images, and they needed to be able to pull them off very quickly. And they wanted to know, do we store them as blobs in an SQL database using SQLite, or do we store them as individual files on disk? And it turns out that you can read these blobs faster, or you can read these thumbnails faster if they're stored in the database than as individual files on disk. And you're thinking, whoa, how is that even possible? Because the database is a file on disk. How can you be reading it faster? Well, here's the thing. If you've got a bunch of files on disk, to read a bunch of them, for each one you have to call open, read, and close. If you're reading that out of the database, you open the database file just once. You only call open and close one time, and then you do lots of reads. And it turns out the overhead of running SQLite to access these blobs is less than the overhead of calling open and close. So it's going to be fast enough for you. Well, but you're worried, well, what about licensing stuff? I don't want third-party code in my thing because I don't want the hassles of keeping track of licensing. We have released all of the SQLite source code into the public domain. And there's a lot of paperwork we had to pull that off, but it is. And that's one of the reasons we have such a small development community. With a lot of open source projects, people can contribute freely, and you can do a pull request. And we don't take pull requests. And the reason for that is, or one of the reasons, is that if somebody sends us some code and we incorporate it into SQLite, then they own the copyright on that code. It's by default. And unless we go through this elaborate legal process for them to release that copyright, that would contaminate the project. So we're very strict about who can contribute to the code. But that means you don't have to worry about licensing problems and possible legal repercussions. Now, yeah, it does say SQLite, and people are turned off by that and think, I don't need a light database. I need a real database, not a toy database. The light in the name is there because I'm notoriously bad at naming software projects. Okay, don't too much weight on that. It's not a big data database, but it will do a lot of stuff. You can have one writer and any number of concurrent readers all at once. And I say one writer, you can have multiple processes writing, that's not a problem. It's just they have to take turns. And the library will queue up your requests for you. But just know that only one at a time is going to be going. You can have gigabyte-sized strings and blobs. The databases can be up to 281 terabytes in size. Now they do have to fit in one file. Good luck finding a laptop where you can store a single 281 terabyte file. Okay, that's going to be hard. 64-way joins, 200 columns for table and index. There's just no arbitrary limit on the number of columns and indices. So you're thinking about, well, hey, I need a database engine for my project. What database engine should I use? Here's a checklist. Yes, is my data remote from the application? By remote, I mean, is it on a different machine? Do you have to go across a network to get to the data? You should probably choose a client-server database in that case. And the reason is the database engine acts as a filter to the data. A lot more information flows from the disk drive or the SSD to the database engine than flows from the database engine to your application. And so if information is going to have to cross a network, you want the low bandwidth chunk to be over the network. And that means that you want the database engine to be on the same machine, the same physical machine as the data. And so that's a good reason. Now, SQLite will work across a network file system, but performance isn't great on a network file system. It really wants the file system to be local. You know, another thing is that a lot of file systems have, a lot of network file systems have bugs in their locking protocol. It's gotten better in recent years. It used to be really bad, and if you hit a file system bug with locking, it could possibly corrupt the database. Do you have big data? And I define big data as any data that's larger than 281 terabytes. So, and do you really need concurrent writers? A lot of people think they need concurrent writers, but when you really get right down to it, if you've got a single disk drive or single SSD, there's one wire that goes between the CPU and the storage device. You're not really writing multiple or concurrently. It's still being queued up. Do you really need it? Sometimes you do, but if you need any of those things, go with client server. If you don't answer yes to any of those questions, SQLite's a much better choice. Where people mess this decision up is that they will say, okay, I don't need any of this stuff. I'm just going to write it directly to the disk. I'm going to write a big XML file or take a bunch of JSON and I'm going to put it in a file that's going to make my database. And you know, when you do that, you can do that if you want to, but you're going to lose all of the transactional capabilities. You're going to lose the query language. You're going to lose the file format that's guaranteed to work through the year 2050. It's just harder to work with. You're going to make your life more difficult unnecessarily. You're going to increase complexity in your application, and complexity is your enemy. So I wrote SQLite, I put it out there, and I thought that it'll be like all the other open source projects I've started, and it'll get 10 downloads per year or something like that. But to my amazement, it went viral. It started going into cell phones. I wrote it in 2000 initially, and the smartphones really didn't come on the scene until around 2006. So this was all starting about then. And so these days, SQLite is found in all of your devices. It's in every phone, your Mac and your Windows machine. They require, they come with SQLite built in, and they require it in order to boot. They will not boot without it. It's in all your browsers, all your bookmarks are stored in SQLite databases. It's in your car probably. It's in all kinds of appliances. It's in the avionics of the Airbus A350. It's in various spacecraft. It's used in everything. It's hard to measure how many uses there are. I think we're pretty safe. There's probably 1 trillion active databases right now. It's probably there are very likely there are more SQLite databases running than all other database engines combined. Some people say that SQLite might be the most widely used bit of software in the world today. My personal opinion, I think that the LiveZ compression library might be a little bit more, but it's certainly within the top 10. So that is a kind of a summary of what SQLite is. I wanted to talk to you today about how it's actually implemented and why do you care? Well, it is a widely used product and you're all experts in databases or will be. And so even if you don't use it yourself, you kind of need to understand how it works on the inside. And maybe you want to make your own fork of it and do something and make it better or something. In which case you kind of need to understand the internals. But even if you don't want to do that, even if you're just using it in an application, if you understand what's going on behind the curtain, you'll be able to use it more effectively. Also, the structure of SQLite, though very different from other SQL database engines, there are common themes that run through them all. And if you understand how SQLite works, then when you go to study another database design, it'll be much more familiar to you. So, the application programming interface. This is not real code. This is pseudocode because I've left a lot out for clarity's sake. But this is looks kind of like a C program, and its job is it takes two arguments. The first argument is the name of a database. The second argument is an SQL statement of some kind. And what this program does is it opens the database, runs that one SQL statement. If the SQL statement's a query, it prints out the results, and then it exits. So let's talk about how this works, because understanding the interface is key to understanding how the thing is put together. So there's two objects you need to pay attention to. There's the SQLite 3 object declared first. It's a database connection. And then there's the SQLite 3 underscore STMT or statement object. That represents a single statement of SQL. We start out by calling SQLite 3 open, giving it the name of the database file, and you get back a connection. Skip down to the bottom and you can see where we actually close that connection. That's the destructor for the database connection. The next statement is SQLite 3 prepare. Given a database connection and the SQL text to be run, we're creating what's called a prepared statement, which is the SQLite 3 statement object. And then the next lines of code are going to run that object. The next line of code is column count. It's just getting the number of columns in the result set. If it's an insert statement or an update statement that doesn't return anything, that might be 0. But if it's a query that returns 5 columns, then it'll be 5. Then we go into a loop. We call SQLite 3 step. This begins executing the SQL. And it executes up until the point that it either finishes or it finds one row of result. If it finds a row of result, it returns SQLite 3 row, or no, just SQLite row. And then inside the loop, we're going to print out the value of that row. I've got a couple of APIs here, SQLite 3 column name and column text. So, and it's looping through the columns, and it's printing out the name of the column and the value of that column as text. And then after it does that one row, it'll call SQLite 3 step again, and it will advance to the next row and do the same thing, and so forth. And when it finishes, it will return SQLite 3 done, and then it returns finalize is the finalizer for the prepared statement, and then we close the connection and we're finished. That's the basic idea. I've left out lots of error handling here. If you're, what happens if you give it invalid SQL? You're going to get an error. What happens if you hit an error while you're running? You're going to get an error. I've left out those details. They're unimportant. The point is kind of this. You can think of SQLite as a compiler for SQL statements. Think of each statement in SQL as a miniature program. And there are two parts of SQLite. There's the compiler that takes the program and compiles it into executable form, and then there's the machine that executes the result. So really, in SQLite, the prepared statement is just bytecode that's going to implement what you've asked it to do via SQL. Now, when we're working on SQLite, we, the developers, we kind of break it up into these 6 components: parser, code generator, virtual machine, B-tree, and pager. So let's go over them one by one. The parser, this is what takes the SQL text, analyzes it, generates an abstract syntax tree. Does everybody, who's had compiler construction, who knows what parsing and an abstract, if you know what an abstract syntax tree is, raise your hand. Okay, that's great. I love it when people know this and I don't need to talk about it anymore. So the parser does that part. You get an abstract syntax tree, that goes down to the code generator, and this is where all what I think is the most fun and amazing magic happens. It has to take this abstract syntax tree and convert it into bytecode. Does all the analysis, the error checking, and that sort of thing. So really, if you think about it, the first 2 modules here are the compiler. And the last 4 modules are the part that run the program. Let's keep going. The virtual machine, it's a very simple virtual machine. I say bytecode, you've probably heard of Java bytecode. Maybe you've heard of, there's other bytecodes out there. P-code, there's a bazillion of them. The bytecode in SQLite, actually here's an example, is a little different. Every instruction has an opcode and 5 operands. It's a 3-address machine. The instruction format is fixed like that because that way we can print it out as a table. I should mention that if you want to see the bytecode for any SQL statement in SQLite, you just prepend the keyword explain in front of the statement and run it, and it will print the bytecode. And we'll talk about this in detail coming up. The bytecode's a little bit different in that with most bytecode, you have things like load some value into a register, add 2 registers together, move the results somewhere else. And SQLite bytecode has that stuff, but it also has some very high level things like create a new B tree, create a cursor into this B tree, seek that cursor to a particular point in the B tree, and that sort of thing. Things that are very database specific. We will go into some details on that in a minute. Let me just point out quickly that in this printout of the bytecode, the stuff shown in gray is only there for debugging, and it's only in debugging builds. When you're in production, those details are left out. Also, I mean, it doesn't actually store the name of the opcode. That's decoded for you for display purposes. And the indentation here that's showing the loop, that's added also. We'll talk more about that later. Now, if you want to play around with SQLite, here are instructions on how to build a debugging version, and you can study this later. The advantages of having a debugging version are that when you're typing in interactively SQL, you can type .treetrace -1, and that turns on lots of debugging stuff that, for example, prints out the abstract syntax tree as ASCII art so that you can kind of see what's going on. And as it's transformed during the compilation process, it'll print it each step along the way. And things like EQP, which stands for Explain Query Plan, EQP trace traces the execution of the virtual machine. So as the bytecode is running, it shows each instruction and the registers that it's using and changing as it goes along. So that's the virtual machine. The bottom 3 layers could be grouped together and be called the storage engine. And it's a B-tree based storage engine. Do you remember that other slide I showed you where we had these databases that were serverless and non-SQL, things like RocksDB and BerkeleyDB? The bottom 3 pieces of SQLite are really kind of one of those. And in fact, if you wanted to, you could go into the SQLite code and kind of chop off those bottom 3 pieces and plug in some other storage engine that you wanted to do. And this has been done multiple times. Oracle once had a product called BDB SQLite. They took the bottom 3 layers off and they stuck on BerkeleyDB, which they bought from SleepyCat, and that was their product. One really famous example of this happening is the database engine called ComDB2. This is open source. It's developed at Bloomberg. Bloomberg is a fintech in New York City, founded by Michael Bloomberg, former mayor of New York, and it's a big thing in the finance industry. And they have a storage engine that is amazing. It runs in multiple data centers, highly redundant. An entire data center can go offline in the middle of a query, and somehow it still manages to finish the query. And anyway, they've got a team of engineers that work on this all the time, but they don't want to mess with SQL. And so what they do is they just pull the SQL part of SQLite out and stick it on, and that becomes ComDB2. So anytime you're doing high finance, you're using SQLite, apparently. So the storage engine summary in SQLite, it is a row store. There are variable length entries, and it's a forest of B trees. We don't, I mean, a lot of SQL database engines, the row content is stored as a heap or some other structure. Everything in SQLite is a B tree. We don't have any kind of storage other than that. Let's go on down to the B tree layer. This is just a B tree implementation. We have two different types of B trees. Classic B trees and B plus trees. You know, there's a bazillion types of B trees. Have you studied this and seen them all and trying to keep track of them all? And they all have names. And the names are not reflective of how they actually work. And so whenever I'm talking about B trees, I have to go pull a book out and say, no, which name was to which? I get confused. But we're using B trees and B plus trees with variable length entries, variable number of entries per page. The pager layer is what's responsible for providing atomic commit and rollback. It's responsible for keeping things ACID. The pager does not know anything about an SQLite database is organized as an array of pages, and they're numbered starting with 1. The first page is 1. There is no page 0. 0 means like the null pointer. And the pages are all the same size, and that size is going to be a power of 2 between 512 and 65,536. And the page number is a 32-bit unsigned integer. So if you take 2 to the 32nd power and multiply by the largest page size, 65,536, you get 281 terabytes. That's the file size limit. Now, if you're using a 4K page, so the page size, every database has a fixed page size, and it doesn't matter what it is. It defaults to 4K because that seems to match hardware the best. If you go with a 4K page size and multiply that by 2 to the 32nd power, then you're limited to a 17.5 terabyte database. That's still more that's going to fit on your laptop, so you're probably still okay. That's for small data, that's right, 4K. So the pager is also responsible for concurrency control and to provide a cache to the B tree. The B tree is only dealing with pages that are already loaded into memory. Then the bottom layer is the OS interface, and this is what makes SQLite portable. This is just sort of it's an object that provides a common way of talking to the underlying operating systems. There are currently 2 operating systems supported: Unix, which includes Mac and Android, and also Windows. We used to support OS2, but we couldn't find anybody who still used OS2, so we dropped that. I hope that we never have to add another one, but because Unix is sufficient for everyone, I think. That OS interface is really an object, and it's runtime pluggable. You can write a new one yourself, you can write a little module yourself, which we call a shim, that has the same interface, that would do something like encrypt the data before it goes to disk, or compress the data before it goes to disk. Or maybe you're debugging, you just want to log what's happening. We use, and you insert this shim in between the real OS interface and the rest of the system, and it continues to work normally. We use this for testing, for fault injection. How do you test a database engine to make sure that it recovers correctly from a system crash? How do you do that? Do you sit there and start something going and then pull the power plug? I mean, that does happen. There are companies that do that sort of thing. But we want to test that we can actually run and we don't have to reboot our machine. So like we have shims that we insert that cause the database file to be damaged in ways that would be typical of the damage you would get if you took an unexpected power loss. And then we're able to see, do we recover from this, and does the transaction either fully commit or does it roll back? So it's very useful for that. So, oh, I forgot to mention, I understand you guys get a break somewhere in the middle of this. When you've heard enough and you need a break, just call out to me, okay? And you know, I didn't mention too, look, if I say something coming up, we're getting into some more detail here. If I say something coming up and you want to push back, feel free to do that. You're not going to hurt my feelings. That's not a challenge, but at the same time, don't worry about it. If you think that this is if I've done something, if you know a better way to do something, speak up. We'll talk about it.
Actually, I just have a question.
Sure.
Have you ever considered bypassing the file system and directly going to the block device?
The question is, have I considered bypassing the file system and going directly to the device? We actually have some code in the source tree that does that. This is I'm going to take time here to tell you, this is a crazy, crazy story. In the United States, we have this thing called a muscle car. Do y'all know what a muscle car is? You know, and all the cars now, they have this little thing under the dash that you plug in, that you tune the engine. And you used to go to performance car stores and they had a little thing that would plug into that, and you could go buy a Dodge Charger and you could plug this thing in and push a button and it would give it an extra 20 horsepower. But then, you know, before you take it into the dealership for service, you need to plug it in again and set it back to the way it was, lest you void your warranty. So anyway, this company approached us, and the little CPU on that thing, they didn't want to pay the licensing fee for the file system that went with it, but all their data was in SQLite, and so they asked us to write an OS interface that talked directly to the SSD. And we have a prototype of that that's in the source tree, so you can do that. I don't recommend that, but you can do that if you want to. So more details. Let's go back up the layer a little bit. All right, how do you do how do you do a layer? You're making changes to dozens, hundreds, thousands of pages in this file. How do you write them atomically? How do you write them such that if you lose power in the middle, either they're all going to get written or none of them are going to get written? That's a tricky problem. I'm going to show you how that works. We've got two, in the file system, you've got the actual data on disk, and of course I'm old school, I call it disk even though it's now always an SSD, right? We understand that. When I say disk, I mean your mass storage device. You've got the disk where things are persistent and they persist across power failures. And then you have a cache of the disk that's inside the operating system, the OS cache. And then you have the information in user space. So when you first boot up, everything's on disk and the OS cache is empty. And you want to read something out of your database. There could be multiple processes that want to read out of the database. So we don't want somebody reading and writing at the same time and overwriting us. So we take what's called a shared lock on the database file, and that prevents somebody from writing stuff out from under us. You know, I skipped a slide back there. I apologize. I'm going to back up a little bit. There are two ways that SQLite does this. There's rollback journals and write-ahead logs. Rollback journals are the default because they work even on network file systems. That's what I'm showing you now, rollback journals. I'm going to show you a second way, which has more concurrency and is faster, called write-ahead log. It's not the default. You can turn it on easily. It's not the default because it requires a small amount of shared memory. And so if you're accessing a database file across a network file system and you're accessing it from 2 or more computers, they can't share memory because there's no memory to share. And so it won't work in that environment. And so that's why it's not the default, but it is faster and is recommended in every case where you can use it. But we're going to go over rollback journaling first. So you do a read, you want to read 3 pages out of the database, and when you do the read call, it pulls that stuff into the operating system's cache, and then you pull it into user space, and you can do stuff with it. So then, so now I want to write to this. So I want to make a change to the database. The first thing you do is take a reserved lock, which tells everybody else, hey, I'm getting ready to write. I don't want anybody else to try and write right now. Just give me a second. I'll be just a second. And then after it takes the reserved lock, it hasn't changed anything yet. It makes a copy of the original content of the pages you're going to change in a separate file called the rollback journal. And it's the name of your database file with -journal at the end. And
that's copying the pages? Or
it's copying the complete content of the original page, because the pager does not know anything about the internal structure of the B trees. So yeah, I know, yeah, could you be faster if you copied only the parts of the page that changed? Maybe, but that would make things more complicated.
That's a bit more like copy and write per transaction or something like
Yeah,
that.
and right. And so this is a simpler way, but it's fast enough, and complexity is your enemy. So we're going to keep it simple. So it copies the entire page. Now it's still in cache. It hasn't made it to disk yet. So if you lose power now, all this is going away. But you can go ahead and make changes to the pages in memory. And I've shown that by these pages being colored orange or tan or brown or something. Now, at this point, at some point you've got to call fsync, or in Windows it's called flush file buffers. Is that the name of the API call? Does anybody remember? I don't remember. I wrote this 25 years ago. I don't remember what it's called. It has worked fine ever since. But there's a call that causes all of the operating system cache to be flushed to disk, and it returns after everything is safely in persistent storage. And at that point, we can take an exclusive lock, and then we can write our changes to the file itself. And when we do the write system calls, it only goes into the OS cache. We also have to do another fsync to push it out to disk and make sure it's safely on disk. And then and only then, we delete the rollback journal. And the deletion of the rollback journal is an atomic operation, and this is what causes your transaction to commit. If at any point prior to this, if at any point prior to deleting the rollback journal, if you lost power, when you booted back up, you might have, say, incomplete changes in your disk file. But you'd also still have a journal file sitting right there beside it. And so when SQLite would start up, it would take its shared lock and then immediately notice that you have that journal file sitting there. We call that a hot journal. We've got to deal with that. And so the first thing it does, as soon as it's starting up, when you call SQLite 3 open, is it takes an exclusive lock, it reads the journal file, and copies it onto the disk, restoring the disk to the state it was before you started your transaction. It rolls it back. And then it deletes the journal and goes about its business.
So the existence of the journal file signals at the same time that something went wrong with the transaction before?
Yes, so the existence of the journal file signals that something went wrong. I got a question in the back.
I'm wondering if the logs are somewhere in shared memory or also in the file, because if photo crashes, then logs, will they still be there or will they be dealt with?
No, locks are not persistent. They're in the operating system memory. They're in kernel space. So if you lose power, the locks vanish.
And you're using the kindness logs, locking feature, like the locking.
I'm not hearing what you're saying. Say again, please.
Are you using the locking feature of the operating system?
Yes.
Okay.
We're using file locks on the operating system. Which, you know, for history buffs, this is really tricky to do on Windows 95, which was the predominant operating system when I wrote this. So
I've heard that operating system logs are not really easy to use on Linux either.
yeah, Linux has its own set of problems with file system locks, in that if you have if you have a lock on a file, if you have two threads and both threads open the same file with different file descriptors, and this guy over here sets a lock on the file, and this guy just closes the file descriptor, it deletes this guy's locks. It's insane. You can tell which parts of Unix and POSIX were developed by the boys at Bell Labs, and which parts were developed by some committee at somewhere, and this is one of those committee parts. Yeah, it's insane. And there are extensions like, it was a big deal a few years back when Linux added, they call it, there's a name for it, but they have a better type of locking where closing one file descriptor does not delete the locks on the other file descriptor. And the name escapes me right this moment. It's not intuitive. What's it called? No, it's not mandatory locking. That's something very different. I'll think of it. I'll think of it later. I haven't had lunch. After lunch, I'll immediately pop to my head. But and we're kind of watching this closely. And Mac has added this too with an incompatible interface. So we're kind of watching this closely. And at some point, we might start using those locks. Right now, there's a lot of logic inside the os.unix.c file to deal with that problem. And we do deal with it, but you have to be very careful with that. Okay, so the preferred form of doing things, if you can do it, is the write-ahead log file. This is much faster, and it gives you more concurrency. And this works as before. You've just got a shared lock on the cache. You read it in the user space. Now when you get ready to write, you can just change space. You can just change content directly. You don't need to create a copy of the original content. Just go ahead and make changes to the pages you have in your private space. But before you write it back to the file, you write your changes into a separate file called the write-ahead log, or WAL. And you'll notice that the last one has a little dot in the middle. That means that's the end of our transaction. There's a special little mark on there that means end of transaction. And we haven't had to do an exclusive lock on the database. That means other people can be reading this while we're writing. That's very important. So, and then some other process comes along and they want to write too. They could pull in a different set of pages, and now when they're pulling these pages in though, they have to know that the WAL file exists. Because if one of the pages they wanted to pull, it looks like page number 2 had been previously modified, and so rather than pull the original copy, it's going to pull the modified copy that's in the WAL file. Well, how does it know that it's there? That was that shared memory part I was talking about. Whenever you're using the WAL mode, every process that opens the database that allocates a small amount of shared memory, which is a hash table, which tells it which pages are in the WAL file and where they're located. So it loads in, so a second process can read this stuff out of the WAL file and do its own thing while these things are being written. And the second process might make its own set of changes, and they'll get appended to the WAL file like this. Now eventually, and if this kept going, eventually the WAL file would grow without bound, and it would be much bigger than the database, and that would not be a good thing. So every now and then, you want to do well, first of all, you do need to sync it to disk. One of the things with WAL is that in its default mode, it does not sync the WAL file contents to disk. It doesn't call fsync. And what that means is that you lose durability. That's the one, the D in ACID. You lose durability. So if you commit a bunch of transactions and you've just written to the WAL file and they haven't been synced to disk, if you lose power, when you come back up, those transactions have been backed out. And that's not durable. And it's not ACID. Now you can set it in a mode where it does do that and you've got fully ACID transactions. But here's what we've observed. Most people don't care. If you're in your web browser and you're creating some bookmarks and suddenly your cat trips over the power cord and brings the power down, Then after you get it booted back up, you're just happy that your bookmark database is still there. That you missed your last 2 bookmarks, you're not worried about that. That's nobody cares. And it is a lot faster if you don't have to sync it after every transaction. So most people don't bother to do that. They're giving up durability for the sake of performance. And you have the options. Is that a question? No, okay, very good. You have a, yeah.
So we're saying so the other process comes in and reads the modified version of the page, and it's kind of a dirty read in a way.
No, because it started its read after the transaction had committed.
I see.
Right. And there are cases where you will want to read an historical transaction, and you can do that as well. Yeah. So every now and then you want to do a checkpoint operation, which is where you take all of the changes that are in your WAL file and roll them back into the main database. And that happens automatically. It just does it automatically by default. If you don't like the way it does it automatically, you can turn that off, and you can have a separate process that does this periodically if that's what you want to do. I don't know of anybody that does that because the automatic mechanism works so well, but it's your option. And then after it rolls all these changes back, it just truncates the WAL file, and then new transactions get appended to the WAL file. There is an issue here where it can only do this checkpoint if there are no, if everybody's caught up, if everybody's using the latest transaction. And you can get into a situation where if you've got a bunch of separate processes all competing and they're doing big read transactions and nobody's ever releasing all their read transactions, it never has a chance to checkpoint, and the WAL file can grow without bound. We call it checkpoint starvation. And there's workarounds about that. We have a branch on the source tree that works around it completely, but there's performance problems. So anyway, that's the job of the B tree. Excuse me, that's the job of the pager. At no point does the pager ever know what this content is. As far as the pager is concerned, it's big blobs. And so we've got separation of responsibility. The pager takes care of your ACID properties. Now we're moving up into the B tree layer, which is your key value storage. A table in SQLite is stored as a B tree. And logically, it exists in the device as just a list of rows. And for most tables, the rows are going to have a row ID, and then it's followed by a bunch of data. And the data is the content of that row in a tuple format. Now, the B tree does not understand the tuple format. As far as the B tree is concerned, that data is just a bunch of bytes. Raise your hand if you're an expert on B trees. How much time do I need to spend on this? No experts on B trees. 1 or 2 experts on it. I'm going to count Jens too. There are 3 or 4 experts on B trees. So I'm going to spend a little time on this. Pardon me?
We briefly talked about it in the lecture, so people from the lecture should have seen it.
You've seen it, but you've never actually coded it. All right. Okay, I understand. Look, there's a lot of stuff. It amazes me, when I first got into computers, my first computer was Apple II serial number 508, and it had 4K of memory, and that included the video RAM. And I could understand absolutely everything that was going on in that machine. These days, that's totally impossible. It is the amount of information you have to know to be productive in this field has mushroomed. I do not know how you can possibly learn everything you need to know in just 4 years. It boggles the mind. So anyway, back to this. A B tree this is a B plus tree is what we're using to store tables. And in a B plus tree, all of the data is in the leaves, but the keys can be repeated. So the upper layers of the B tree consists of pointer, key, pointer, key, pointer, key. There's no data in the upper layers. So from the root page, you have to follow it all the way to the leaves in order to get to the data. The keys appear more than once, which is okay, because now the row ID is a 64-bit integer, but we use a variable length integer encoding. So for small integers up to 127, that's just a single byte. If it'll fit in, up to
7-bit encoding?
pardon me?
Is that 7-bit encoding?
7-bit encoding, yes. And so in the worst case, it'll use 9 bytes to store the integer. But usually, these row IDs are 2 or 3 or 4 bytes. They're pretty small. And you can put an enormous number of them on one page. And so we see fan outs up into the thousands. So technically, if you're looking up a row in a B tree, just purely technically, it's a logarithmic time operation because you've got to do a log number of steps to find it. But the fan out on these things is so huge that it feels like constant time. So, yeah, the query planner, when it's evaluating it, it does figure the log in there, but really, for practical purposes, you could call it constant time and it would work really well. So this works pretty well. The other thing you may have noticed here is that I say all the data is in the leaves, and in this diagram I'm showing 3 rows on one page, and let's say the page is 4K. But I said that it would hold blobs up to 2 gigabytes. How are we compressing 2 gigabytes into one 4K page? Well, if the data won't fit, we have overflow pages. So at the end of the data area, there's just a number of another page which you jump to for more data, and it's a linked list. And my instinct would be that this is a really crummy way to do very large blobs. And I did it this way because it's simple, and because when I was designing the file format, I looked around at every SQL database I could get my hands on, and the biggest string or blob I could find was about 2K. So I thought, you know what, a linked list is going to be fine. Now we routinely use SQLite databases to store multi-megabyte blobs. That just happens all the time, and it works fine. You'd think that this linked list format would be inefficient. I have no explanation for why, but it seems to work fine. On the page itself, you know what, just for the interest of time, what time is it? And, oh, I've got a clock over here. I've used an hour. I'm going to skip this page. It's not important. It's just low-level details. An index is stored as a traditional B tree. And furthermore, the key for these B tree entries is the value of the index. And we're not using any payload. We're not using any data for the index. For an index, the key is the data. And I'll show you how this works in a little bit. So it's arbitrary linked keys. The B tree layer doesn't know, the keys are in the tuple format, and the B tree layer doesn't know what that format is. So the virtual machine hands it a pointer to a comparison function so that it can make sure they're in the right order. Okay, all right, listen, full disclosure. Actually, there are some optimizations in the B tree layer that it might know a little bit about what the tuple format is, but that's, we threw that in there because it makes it run faster, but it makes it messy logically. So let's pretend that doesn't happen for this lecture. So in a B tree layer, the keys only occur one time. There is no data. In a complete database, there's one B tree for every table and one B tree for every index. And they're all in that same one database file. How are they arranged? Well, I mean, if we know the root page of a B tree, we can always find all the other pages of the B tree by following the child pointers. And so these B trees are actually kind of interspersed throughout the file. In this diagram, I think I have 2 pages that are not even being used, page 4 and page 8. They might have been used at one point and we deleted content, and now they're free pages, and they'll be reused again as a B tree needs to grow. But the B trees can be all over the file. All we need to know in order to get to the data is the root page of each B tree. And so the question is, how do we know what that root page is? Every SQLite database has a single table called SQLite Schema with 5 columns, which are the type of object, the type of schema object, and that's going to be text, table, index, trigger, or view. The name of the object, the table it belongs to, if it belongs to a table, and then the root page. The root page of the B tree that describes it. And that's going to be null for views and triggers because they don't have storage. But for indexes and tables, that's going to tell you where to find its B tree. And then finally, we store the original SQL text of the create table statement or create index statement that created this object. So every time you open an SQLite database, one of the first things it has to do, oh, I forgot to mention, the schema table is always rooted at page 1, so we know where to find this one. So whenever you open an SQLite database, the first thing it does is it goes to page 1 and it scans that table and it looks at all of the objects that are in there and it builds its own internal symbol tables showing it all the tables and indexes that it understands and goes from there. You can actually see this yourself. You can go online to sqlite.org/fiddle. Fiddle is SQLite compiled to WASM or WebAssembly, and so it's just going to be running SQLite in WebAssembly on your browser. And you can type in create table T1 of X, and the dot mode Q box is just setting the output formatting. And then select star from SQLite schema, and you can see that table T1 is rooted at page 2, and there's its original text. So back to the virtual machine, what is the tuple format? The tuple format is used for the content of tables and for the keys and indexes. You need to understand the variable length integers, and yeah, it's a 7-bit encoding. Looking back, I could have chosen a better encoding there, but it is what it is. We're going to talk about the tuple format in SQLite, and this is one of the more controversial subjects. I think it's a feature. Some people think it's a bug. You can form your own opinions. The tuple consists of a header and content, and the header is just a sequence of integers. If there are n columns in the tuple, then there'll be n plus 1 integers to begin it. And the first integer is just the size of the header in bytes, including that size integer itself. And then the other integers tell us what the data type is for the values of the tuple. And they're all the variable length integers. And so they're normally they can be very big, but they're normally only 1 byte each. Sometimes you'll see a 2 or a 3 byte integer, but they're normally just 1 byte each. And this is the code used to determine what the data type actually is. So if the type integer is a 0, that means that tuple value is a null, and it actually consumes 0 content. If it's 1 through 6, that's a signed integer of various lengths. If it's 7, it's a floating point number. 8 and 9 are integers 0 and 1, which we learned are very common. For blobs and strings, that's going to be a value of 12 or greater. Even values for blobs, odd values for strings, and there's a formula there to figure out how many bytes are in the blob or the string. So we have this header, and it tells us everything that's in the tuple and its data type. And that's followed by the data itself. Here's an example. Create table T1 ABC, insert 177 null and hello. And you can see there that it's a 4-byte header, so the first byte's 4, and then the second one is 2, that means a 2-byte integer. And the third one is 0, which is a null, and the fourth one is 23, or hex 17, and that's going to be a 5-byte string. And then following it is the data. It's a very efficient encoding. It's self-contained. And here's the big deal. You don't have to, it allows you to put arbitrary data types in any tuple. And as a result of this, or actually this, because I wanted to do this, that's the way I designed the tuple format, SQLite does not require you to specify data types on your columns. You can create a column with just the name of the column itself and put any data you want into it. And I consider this a feature. I think this works really, really well. I get an enormous amount of pushback from telling me that this is a bug and needs to be fixed. So you can form your own opinions.
The database professor comes in and says, you can...
Yeah.
No!
Relational theory purists in particular, their heads explode with this, okay? So...
Okay, but let's phrase it in my language. So basically, you have a key tuple store, where every tuple will have a different format, right?
Yep.
And the schema, you annotate the table with visual thinking, but it doesn't mean anything.
Well, it does mean something. So in order to be compatible with other SQL database engines, if you declare a column to be text, say, and you try and store an integer in there, it will convert the integer into text. Postgres does the same thing. So it will try and cast it if it can do so without losing information. But if you have a column that says integer, and you try to store text in it, and that text doesn't look like an integer, it contains the alphabetic characters, it will store it as text.
Okay, what about the number of attributes stored versus the examples?
Like what you varchar 20 or something?
No, the number of columns basically. If you have 3 columns
No, we do, yeah, you have to specify the number of columns. You can't store an arbitrary number of columns. I didn't go that far. Didn't go that far. You know, really, people say, oh, well, but this will cause bugs and stuff. You know, the only bugs that we've ever seen from this are when people write their application initially in SQLite, and they take advantage of this flexible typing scheme without realizing it. And their application works great, and then they go to port it to MySQL or Postgres, and it stops working on them. Okay, that's the only problem that we ever have with this. So it's not a source of bugs, it's a source of freedom, of flexibility. People like to use the term strongly typed or type safe, you know. I like to refer to other databases as judgmentally typed. So, yeah, you can choose. I do get a lot of pushback on that, and if you think that's a crazy idea, please know that you're in good company. But the part of the database engine that I personally enjoy the best myself is this code generator thing. And there's a lot to generating code or transforming an SQL statement into bytecode. You've got to transform the tree to make it more efficient. You've got to determine the join order. You've got to select indexes, and then we generate the bytecode. I've kind of, in this diagram, I've kind of given you the source code files that do these sorts of things. If you want to go explore yourself and see the details of how we do it, those are hints to you of which source files to look in. But really what I talk about is how I'm going to give you a high-level overview of what the algorithm I'm using actually is. So the first step is of course we have to resolve the table names and column names and issue errors if they don't exist, resolve the views, expand the star and select star. Flattening subqueries, that's an interesting feature. But my next slide is on, I'm going to get rid of a lot of the syntax here by, there's a lot of join syntax in SQL. There's, natural joins, and there's usings and ons and stuff. Everything goes into the where clause. So the first thing one of the early things that I do is, when processing this syntax tree, is I convert a natural join into a join that it uses a using clause, and then I convert the using into an on clause, and then I convert all of the on clauses into a where clause. And you say, well, for an outer join that doesn't work. Well, but see, I've got a syntax tree. I can put special tags on terms of the where clause to say, hey, this came from an outer join, and so it'll still work. Another important step, and the single largest source of bugs in SQLite probably, is the query flattener. And this is a thing that takes subqueries and tries to merge them in as joins in the outer query. An example, and this comes up a lot because if you've got a view, the way SQLite handles views is a view is just, it does it by substitution. It just takes the text of the view and inserts it into the query. So If you've got a view and it wants to expand it, it would like do this transformation that you see listed here. We have things like push down optimization. What I've found is that push down is a badly overused term. Push down refers to any of a great many number of things. When I say push down though, I mean we take where clause terms from outer queries and push them down into subqueries, possibly helping the subqueries to run more efficiently. That sort of thing. That's all great. That's all a lot of fun. Is that the proper term, predicate push down?
Push down, the other projection push down, but I would say predicate push down. One condition, a filter condition you push down somewhere down to the source.
It's called predicate push down. That's good to know. I will go change the comments in the code. That's good to know. That's why I do these talks, because I learn stuff like this. Look, here's the scoop, is that, well, I said at the beginning, I wasn't trained in, I didn't grow up in the database world. The database people were at MIT, Harvard, Berkeley, Saarbrücken, and I didn't live near any of these places, and I went to my local university library, and there was nothing there on it, and I had to invent a lot of this stuff myself. And it's really interesting. I've lectured at all of these other places and talked with all these other people. I mean, I've had conversations with Stonebreaker himself, and it's really interesting. We came up with the same solution, but of course we use different names for it. So I've had to, as we've gone along, I've had to adjust my vocabulary. So now I'll go change push down to predicate push down. Thank you for that. SQLite only processes joins from left to right. So the joins have to be in that format. If you have a query like this, and of course, if they're all inner joins, it's trivial to arrange it in that left or right format. If you've got an outer join, you can't freely rearrange them. And if you have something like this, what SQLite does is it materializes the one on the right, and then it does the join on the materialization. So that's a limitation. You'd say it's a limitation. Maybe in the big table, in the big data world, this would be a serious drawback. But for the kinds of queries that run on phones, it's really not a problem. This just doesn't come up.
Do you keep the order as specified in the SQL query, even on the?
No. If there are inner joins and we're free to reorder them, I reorder them with gusto.
But is there any cost-based?
Cost-based. I'm coming to that. Don't get ahead of me. I'm just not there yet. So this is kind of a high-level schema of how I implement the joins in bytecode. I'm going to show you actual bytecode coming up in a minute, I believe. At the beginning, we open a bunch of cursors. There's a cursor on every table, plus whatever indexes we need to use. And then we position these cursors so that they're pointing at all the rows that are being joined together. And then we use those cursors to pull out the result set for our single row of results. And then we advance the cursors to the next row, and we keep doing that until we run out of rows, and then we end. That's kind of the very high-level schema. Now, for the next slide, I'm going to show you is actual bytecode, and we're going to talk through it. If you want to do this yourself, here's the code you have to type in. And I had to, in order to show you this nested loop join, I had to disable an optimization, because SQLite does not like to do these unindexed nested loop joins, and it will go in and do optimizations to prevent it. So I had to disable that in order to show you. So here is an actual query, a three-way join. And again, the grayed out parts are things that would not normally be in the bytecode, but I've inserted here just for legibility. And the indentation, of course, the bytecode doesn't care about indentation. It's a stupid machine. The indentation is inserted for us humans, and it makes it easier for us to read. So this is a three-way join, and there are no indexes used. So it opens three cursors on the three different tables of the join. At instruction 5, it rewinds cursor 0, which is the cursor on table T1. so that it's at the very beginning. And then on instruction 7, it rewinds cursor on T2 to the beginning. And then at that point, it can evaluate the constraint T1b equals T12, and it evaluates it. And if they are not equal to each other, it skips over the rest. But then it does a loop over T2, and it does the constraint on T2. And then in the green code is where it pulls out the values from the various cursors, and then it calls this instruction called result row. And what result row does is it stops the virtual machine. It stops right there. And it causes the SQLite 3 step function to return. And to return a value SQLite row. It's paused. And then the application calls things like SQLite 3 column text and gives it a column number. And what that API does is it actually reaches into the memory, into the registers of the virtual machine, and pulls out the value and returns it to the application. So the application does that for a while. It calls SQLite 3 step again, and then execution continues on down. We hit the next operator, which advances the cursor to the next row, and you can see it's 3 nested loops. Of course, this is wildly inefficient. We wouldn't want to do that. But all of the joins follow the same pattern. Here's an example of how we do a left join, for example. I just added a left join on T3, and you can see it's exactly the same code except for it inserted these extra 5 lines. Like on instruction 12, it initializes a match flag to 0, and then if we ever get a match on the T3 table, it sets it equal to 1, and then after we've finished processing the T3 table, if we never got a match, it calls on instruction 24, it calls null row on the T3 cursor, which means that any subsequent attempts to pull content out of the T3 cursor will return a null. And then it goes back and it generates 1 row with T3 equal to null. So that's how you would do a left join. Now suppose we had an index. Here's a 2-way join, and we have an index on T2C. So now we're opening 3 cursors still. One of the cursors being opened is a cursor on the index itself. Cursor 2 is on the index. So it looks like T1 is in the outer loop, and we're having to loop over the entire value of T1. And so we rewind it at instruction 5. Then in instruction 7 through 9, we're searching index T2C for entries that have T2C equal to T1b. And for each one of those, at instruction 11, we're then moving the cursor 1 to the particular row that index pointed to. And then we get it back into the green where we pull the columns out of the cursors and return them to the application. So you can, remember, you can put explain in front of any SQL statement and it will give you this stuff. And you can work it out yourself. And if you want to, you can get on Fiddle and you can try some interesting things such as range scans, constraints involving in operators or connected constraints, full outer joins, that sort of thing. I'm not going to show you any of that stuff here because it won't fit on a slide. It can get very big very quickly. I just want to talk, the rest of my talk here, I want to talk about how does it pick the order of the joins. Just to review, the query plan it's nested loops over cursors. 1 loop for each from clause. And the interesting questions are, what is the best nesting order for the loops and which indexes should be chosen for each loop? To do this, I have an object that I call a where loop, and I create a bunch of these. You're going to see them in a second. And for each where loop, we have a specific term of the where clause that we're talking about. We have prerequisites for that loop. In other words, what other loops have to be in outer loops because we're using data that those other loops contain. the type of loop. It can be a full table scan, a primary T-scan, a secondary index, a query time index. There's a bunch of others we're not even going to talk about. And then we have some cost metrics for that particular loop. Setup cost is a one-time cost. It happens one time. And this is normally only used for query time indexes. A query time index is like a hash join, where you have to first go through the table and build a big data structure to tell you where to look. It doesn't come up much, but it does come up. And then we have a cost per iteration of the loop and an estimate on the number of output rows. Now, all of these costs are stored using logarithmic values. I do all costs as a 16-bit signed integer. And part of that is because when you're doing these kinds of cost-based query computations, the predominant operation is multiply. And if you're storing it logarithmically, you can just add. And surprisingly, I thought with modern chips with 15 gazillion transistors that floating point multiply would be just as fast as an integer add. And I was wrong. But when I changed from I used to use doubles for this, and when I changed to using these 16-bit integers, it got measurably faster. So costs are stored, they're imprecise. It's 10 times the log 2 of the value is what I'm storing. And this is imprecise. We can't be very exact with these 16-bit integers. But here's the thing. These cost estimates that we have that we're using in our cost-based query planning, they're guesses. They're not real. They're not precise. And even though this 16-bit integer doesn't give you an exact number, it's probably more exact than your actual estimate is, and it's going to be fine. And this works out fine for us. So all of the numbers you see are going to be small integers, even though they represent actually very large numbers. Here is an example of how we plan a query. It's a simple query it's a two-way join, and there's a single join constraint, and we assume that there's an index on B1. We got 4 different where loops. We could run a loop over table A that's a full table scan, and if you're doing a full table scan, there is no prerequisite. Or we could run a loop over table A if we know what the B value is already, and so B is a prerequisite, and if we had a query time index on A2, because then we could use the B1 equals A2 constraint to look it up very quickly. And you can see the cost on that one has a very large setup cost, but a much smaller per iteration cost. And then on B, you can always do a full table scan, and then but if A is in the outer loop, then B can be much faster. So the best query plan in this case is just an ordered list of entries such that there's exactly one entry for each from-clause term. All prerequisites are satisfied, and it has the lower cost. In this case, it's pretty obvious. You can just look at it. It's A0, B3. This, you look at this and you say, this is really a graph algorithm. This is kind of the traveling salesman problem for directed graphs. Yeah, it is incomplete. It is, but we'll get to that in a second. How do you compute that table? It's really simple. You take each term of the from clause and you go through and you start adding where clause elements to it, or where loop terms based on that from clause. So for each term in the from clause, you always add a full table scan. You hope you never have to use it, but you always add one. If it's appropriate to add query time indices, if you have constraints in the where clause, you add query time indices. If you have constraints that would satisfy primary key, you add that. If you have constraints that would be useful to a secondary index, you add those. And all the time you're doing this, you're also purging out other where terms that could not possibly help you. Let me just very quickly, here's a three-way join where I've got, in the on clause, I've got a min function. And here we have a where loop that has two prerequisites. Number 7 has two prerequisites. And I show you this only to say that if everybody has at most one prerequisite, you can draw this thing as a graph and it comes with a graph algorithm. But in general, it's not, because sometimes you have multiple prerequisites. The plan I really want to show you is this one. And this is a query that may be familiar to your professor. Do you recognize this one?
Oh, it looks familiar.
Yeah. Because I took this directly from your YouTube video, okay? Now, in your YouTube video, you did not give me a schema, so I had to make inferences about the schema.
Okay.
But this is yours. And I put this into SQLite, and I ran it, and these are the where loops that I came up with, that it came up with. And I'm just showing them here for you. I'm going to go into more detail, and we're going to walk through this example very step by step. But for now, just know that these are what they were. And the best plan is DBAC. And you know, I didn't go back and check your video to see what you got. I don't remember. But that's how that query is planned. And notice this is the code that actually gets generated here. And notice in this case, it's like there's only one loop. You can just see that immediately from the indentation. There's only one loop. Really, there are 4 loops here, but the 3 inner loops are constrained by primary keys or unique indexes. And so they can only execute either 0 times or 1 time. And so they're kind of not really loops, it's just fall through code. So we're opening a bunch of cursors at the top, 5 different cursors. D is in the outer loop, so we're doing an indexed lookup of some entries on D, and then as it goes on down, it does indexed lookups to other tables, and finally at the bottom, it pulls the results from the cursors and outputs a row. So how did we get this? Now when we're the first step, of course, is coming up with all the where loops. And this is the complete set of where loops that it generated. But the ones and X's we can eliminate without further consideration. So for example, up on top, a full table scan of A. We also have another where loop that has no prerequisites on A that uses the index, and that's always going to be faster than the full table scan. There's never a reason to think about a full table scan on A, so we can just eliminate that one. There's no point in generating a query time index on A1 because we already have a secondary index on A1. There's no point in doing that, so we can eliminate that one. And so forth and so on down the list. A lot of these where loops can be eliminated without further consideration. We'll just get rid of those. And and my costing here, I did not populate the database with data in order to do the costs and then run analyze. Typically you would have a variety of costs, but here, because I don't have any knowledge of what's in the database, it's kind of some standard weights that it throws in when it doesn't know anything, standard guess. Here, on this slide, I just moved it out to get it out of the way. Here's our where loops. The first step of the algorithm to find the best query plan is to find paths through this that have just one table. And this step is really easy because you just pick the where loops that have no prerequisites. Okay, and these are optimal plans that only do a single table. Okay, based on that, we then start building up our paths of length 2. And these are plans that deal with 2 tables. Let's just look at A first. We're going to add on to A all of the B's that work. We can add number 2 because number 2 doesn't have a prerequisite. We cannot add B3 after A because B3 has a prerequisite of D, and we haven't seen D yet. But we can add B4, we can add D5, we can add C8, we can't add any of the others. Okay, very good. And then the next thing we're going to do is we're going to observe we have 2 entries on this path thing of AB. and we don't need 2 entries. We're going to just pick the lowest cost for A, B. And we're going to eliminate the highest cost and get rid of that one. And now we're going to do the same thing for B. We're going to add everything to B that we can. And once again, we will go back and look for things that can be eliminated. Notice here we've added B2A1, which has a pretty low cost. And that enabled us to eliminate A0, B4. Because when you're eliminating higher or unnecessary or redundancy, it doesn't matter which order they occur in. Now the order that they occur in matters in the solution, but when you're removing duplicates, the order does not matter. So we eliminate A0, B4, B2A0, and B2D5 because, we eliminate A0, B4, and B2A0 because those are higher cost than B2A1, and we eliminate B2D5 because it's a higher cost than B2D6. And we do the same thing for D. And there's a bunch of new eliminations we can do. And then finally C, and it turns out with C, none of the plans that start with C are really going to survive. So we're just going to head and eliminate all those. And so at this point we have the optimal paths of length 2 for solving this join. And we just repeat that process again for paths of length 3. And then paths of length 4, and then we have our solution. Now I said earlier that finding an optimal solution here is NP complete. And I just found an exact optimal solution. Does that mean that I have solved P equals NP? No. This only, there's only 4 tables here. And so this only blows up and becomes exponential as you add larger numbers of tables. And so we do have to limit the size of each path step. At the end of each step, we only allow a certain number of paths. And if you have a large join and you don't restrict it, you can get an exponential number of paths at each step. Now, the latest version of SQLite, the latest released version, limits the number of paths to 10. At each step, we take the 10 lowest scoring paths. Where did 10 come from? Did I just make that number up? Actually, I didn't just make it up. 10 is the least number of paths that I need in order to get the optimal solution for TPCH. It turns out that somebody on the report on the forum, they went to their relational theory class and they were doing something, and they had this just monstrous star schema, and it's like a table with 100 columns in it, and they created a separate index on every column and a dimension table off of every one. And they found a solution where 10 was not enough. So in the next release, if it sees you're doing a star query, it's going to go up to as many as 18. But that's a heuristic. And by limiting it to 10, we keep this, I think it's n squared to do this. I haven't actually done the detailed analysis, but it's a reasonable amount of time. That is how the queries are planned. And I'm finishing up, I think, right on time. I just got a summary slide. SQLite. It's in-process library, one file database, power-safe transactions, a row store, not a column store. Everything is in a B tree. There's no heap. Always B tree local. No hash tables. The schema is stored as a bunch of create table statements. We don't have a, what do they call it when, the buzzword escapes me, when you've got this elaborate schema that gives you your schema. And then it's all done with bytecode, and we do query planning by solving the traveling salesman problem. Not really, but that fit nicely on the slide. What questions do you have?
Thanks. Questions?
Yes, sir. What is the licensing of SQLite? It's public domain. You can take it and do anything you want with it.
Even sell it.
Yes, you can even sell it. We do have a trademark on the word SQLite. So if you want to take it and sell it, you'll need to rebrand it and call it Saarland DB or something. I don't know. But other than that, there are no restrictions.
One question, I mean, on the web page, there are like 3 developers. SQLite is so widely used on the planet.
Yeah, we have.
For whatever weird reason it breaks. If you introduce you have a bad day, you didn't have your coffee, you introduce a stupid bug in the production with SQLite, and half of the internet breaks down. Is that a reason?
Yeah, so well, I'll come to you in a second. I'm going to answer this question. Yeah, this started coming up when Nokia started using SQLite in their cell phones, back when Nokia was the world's leading manufacturer of cell phones. And they called it bus factor. The management got together and said to me, Richard, you need to increase the bus factor of SQLite. And I thought, what is that? And they explained to me the bus factor is the number of people who have to be hit by a bus in order to stop all development. And so I started the SQLite Consortium, and Mitchell Baker, who's the woman who runs Firefox Mozilla, showed me how to set this up. And so there's a number of companies that contribute support to us so that the developers can work full-time on this. Actually, there's only 2, it's just me and Dan do most of the work. There are 5 committers total, but we do most of the work. And that's okay. The more people you have, I mean, Fred Brooks discovered that, adding developers to a project does not improve your schedule. It just increases your communication cost and things slow down. It is all open source, so if anything breaks, then, somebody else can presumably jump in and fix it, right? We do have very extensive testing. We do aviation grade testing. And so, and that reduces our need for people. Yeah, you had a question.
Actually, I wanted to respond to Ian's question because
okay.
I remember I was listening to a podcast where Kevin Gaffney was interviewed. Do you know it?
I do not know Kevin Gaffney.
So he's been working on SQLite for some time, and he's been giving on a podcast show some insights into SQLite, and he said that's like one of the best tested systems, like software systems in general. Like you have like 100% line coverage almost.
I do. Oh, no, I have way better than that. I have 100% branch test coverage.
Or even that. So you're hard.
Yeah, line coverage is easy. Branch coverage is hard. Yes. No, actually, when we were scheduling me to come and talk, this talk was originally supposed to be about how it's tested.
Yeah.
And I have that talk right here. It's an hour and a half.
We can move to a different lecture.
We'll move to a different lecture hall for that. But then Ian said, no, let's switch over to this other one because that's going to be better for the students. So, which is fine. That's fine. Well, I'm happy to give that other talk to you in a little bit. Yeah. Testing is a whole nother kettle of fish. What's the question here?
2 actually. So on the technical side, do you also maintain bind libraries for SQLite? Because I imagine that the philosophical clashes regarding type safety can get very interesting when you're talking to somebody, for example, who wants to use SQLite or Python, where strings, for example, don't really have a native encoding.
Yeah. So no, really, I was really big into the TCL scripting language, and I was a member of the TCL core team when I was writing this. And so I often say that SQLite is a TCL extension that escaped into the wild. So I do maintain the TCL extension. We've recently added a JNI extension that Stephen Beal, who's in where? Near Brandenburg, here in Germany, does that. But most of the extensions are maintained separately. And there's multiple Python extensions. There's the one that's built in, but then there's a lot of others, and people say, oh, well, mine's better because of this and that and the other. Roger Benz is big on one of them. He thinks, and I kind of agree, his is better for Python. But no, we try and make it easy for extension writers, but I do not maintain them myself. I have enough work as it is. Thank you very much.
The other question is like more a personal one. So I heard that you basically did a PhD, but then you decided to go off and instead build something amazing, or like instead of pursuing academia further.
Yeah, so when I graduated with PhD in computational linguistics, which is kind of useless, in 1992, there were literally 500 applicants for any tenure track position. Literally 500. And I knew perfectly well that my application was going to be near the bottom of the stack. So look, and it really, I'm just not a good fit for the academic world. I like to write code, not papers. And this is not to put down academia in any way. It's just not my thing. I would not have done well in academia. I really like teaching. It's a lot of fun, but I would not have been very good at it. And my preferred mode of working is to lock me in a room with a computer and leave me alone. And that's kind of what I do. I come out and give talks like this, but most of the time I'm just in the room coding. And that's what I like to do, and I've really enjoyed doing it. And so for the first 12 years after I graduated, I did freelance software development for people, solving hard problems. And that was a lot of fun. But then SQLite took off, and now I do that full time. I never imagined that I would be a database guy. That was never my intent, but it's been a lot of fun. I've had great fun doing it. Other questions?
So just to clarify, if anybody's wondering, if you join my group, you can do both, write papers and write code.
There you go. Yes, sir.
If there was if you had the chance to change some fundamental architectural side of SQLite, redo things with all the experience you have now, is there anything you would change from the design perspective of SQLite?
Not major changes. Now, when I was going, even small changes, like the variable length integer format I chose, I could have done a much better job at that. That chart that you had, that I showed you that had all the types based on numbers, I could have done a better job of that chart. The way that information is laid out on a page of the B tree, I have like a header and then content follows it. It would have been better to put the header at the end rather than at the beginning. Would it have been a footer then? I'm not sure. But if you put the constant information at the end rather than the beginning, it makes it, you can process things much faster without risking overflowing and causing an array bounds overflow even on a malformed database. And I could have gotten performance benefits that way. So there's a lot of little things like that I might have changed, but I was very fortunate, and I made some good architectural decisions from the beginning, I think, that for the most part it's worked out really well. And I'll admit, a lot of cases I was lucky. Dodged that bullet. Any other questions? Yes, sir.
How does security work for SQLite? For example, I know that it's not a good idea to let users run arbitrary queries on my database. But would everything break, for example, if I let users run arbitrary bytecode on my database?
Well, there's no way to run arbitrary bytecode. We do test SQLite very carefully using fuzzers to make sure that any combination of malformed or correctly formed SQL and a malformed or correctly formed database will not cause a memory error. You might get goofy answers, but you're not going to get a memory error. That's our promise. Now, if you have access to the C API, well, then all bets are off. Because if you can call a C function, then you already own the system. It doesn't really matter, right? But it is proof, it is secure against attacks using SQL or malformed database. Now, you can certainly write a perfectly legitimate query that takes so long to execute that you could execute a denial of service attack. But that's just kind of the nature of SQL. I can't fix that.
Other databases can do that too.
Yes.
Okay, thanks again for the super interesting
thank you for allowing me to come and talk. Thank you very much.